This was lab 1 of constant velocity over time. The purpose of this lab was to model the differences between the experimental object of the toy car moving at a constant velocity and the computational model. There were possible experimental discrepancies, which I will talk about later. The object we are studying is the system, which is the toy car, and everything else is the surroundings. This lab was based on Newton's first law, which mainly said that an object in motion remains in motion unless acted upon by a net force. And we assumed there was no net force, so there was a constant velocity. The net force is equal to the change in momentum over change in time, according to Newton's second law. And the change in momentum is equal to mass times change in velocity. So since there was no change in velocity, there was no change in momentum, which resulted in a zero net force, and then this resulted in the constant velocity in the velocity update formula, because final velocity equaled initial velocity when there's zero net force. And then the position was updated with the position update formula with the constant average velocity. The initial position was 0 in all directions, and the initial velocity in the x direction was 0.5 meters per second. This was the model of the forces, which canceled out of the normal force and the gravitational force, resulting in a net force of 0. And the main result was both the experimental and computational model were similar in the constant velocity, except the experimental increased at a higher rate in position towards the end due to discrepancies in other possible forces and errors measuring the change in position over time. This was the experimental model using the tracker analysis that tracked the position over time. These were the experimental data of a frame rate of 0.033 seconds, the mass of the car was 0.04 kilograms, and the diameter of the car was 0.1 meters. The initial velocity was calculated with the initial position and position 1 through displacement over change in time, and the final time was 0.4 seconds, so that's how long the object took to move across the screen. So this all was put into the computational model too, to model the predicted values, and these were the initial conditions with the initial velocity and position, and then the delta t, which is the frame rate. These were the velocity update and position update equations that are put into the coding, and so you can see that the ball.vel is how the velocity was updated, and then ball.pos was how the position was updated. This is the iteration that allowed the velocity and position to update over time, and then the net force was equal to 0. And this is all for time is less than 0.4 seconds, which is length of the video, and this was the delta t that advanced the clock. These were the results of the computational model that calculated the position versus time and the velocity versus time, which was constant. And then these were the results comparing the computational versus experimental model, and the experimental increased a large amount towards the end, as you can see, so it's not that constant. So he had the same initial position and initial velocity, but the experimental was probably influenced by net external factors. So their possible sources of error include other net forces acting on the car, errors in tracking the car with the tracker software, errors in placement of center of mass of the car was not accurate, and it could have had motion in other directions. So what if the axes were flipped? Right would be the negative x direction, so it would increase in a more negative direction, and the magnitude of the velocity would still be the same. The velocity would just be negative, so like the position versus time graph would have a negative slope. The position versus time graph would be reflected across the x-axis, with lines sloping up and to the left. But still, there would be no net force. Is it possible to say how many forces are added together to give 0 net force? No, it's too difficult to actually see all of the forces acting on the objects, because there's like an endless amount that it could have had. So it's not possible to see how many forces are added together to give 0 net force. It's only possible to see like the main ones, which are the normal force and the gravitational force. Thank you.